welcome back. Let's talk about calculus with the polar coordinates. Now I'm going to be very honest, very happy to be in our last video of polar coordinates, as I said last video, but yeah, there's lots of applications of it, so can't really complain. The applications are more of a circle type of thing, but why don't we get into more complicated stuff, because why not? Anyways, let's hop right into it. So first things first, derivatives. Now, we know that we can have a function r of theta equals whatever, and of course we could find dr d theta, and this would tell us how fast is r changing with respect to theta, or over theta, which is kind of useful. I'll illustrate it for you. I mean, it's useful in a mathematical sense, but in a real world engineering type of sense, not so much. So let's say we had our function of theta, function r in terms of theta. I mean, here we would have a positive rate of change right down here, because our r value is getting larger as theta increases this way. And so that's what dr d theta is telling us. But what if we wanted, and I always forget my x's and y's, but what if we wanted dy over dx? This might seem as a daunting task, but all we have to remember is that y equals r sine theta and x equals r cos theta. And for that reason, we can use something like the chain rule. And I say something like the chain rule because it's not really the chain rule, but it kind of is. It's got the same idea. So of course this would show us what's the slope of that line. That would be a straight line. This would be dy dx at this point. And so how would we find dy dx when we don't have y's or x's in our equation? Well, let's remember these equations right here. These are our friend. We know we have an r of theta, so we can still use this. Y equals r of theta times sine of theta, and x equals r of theta cos of theta. It's the same thing. It's just now we have a function. So these are really y of theta equals r of theta times sine theta, and x of theta. So they're kind of like parametric equations, and I'm sure you guys can see some correlations between parametric equations, polar coordinates, especially in the unit circle and things like that. So what you might notice now is that we can take dy d theta and dx d theta, and that helps us out because we can easily find dr d theta. So let's just remember we have dy over d theta and dx over d theta. But we want dy over dx. Now if we remember the chain rule, we can find dy over dx using a, I guess you would call it intermediate variable, say u, where you'd have dy du times du over dx. And so what we can do here is we can say dy over dx equals dy d theta times d theta dx. But we don't know d theta dx. But we do. Really what this is dy d theta times, or I'll use brackets actually, d theta over dx to the negative 1. Right? It's just the reciprocal. And so what we can actually say now is that dy over dx is equal to dy over d theta divided by dx over d theta. Where our y's and x's of thetas are these equations right here. And so that would be a very long problem if I was to go over a example. So let's just cut this video a little shorter and hop into integrals. So what we can do with integrals is, of course, we could, a good example of an integral would be the area of a circle in polar coordinates. But for polar coordinates, there's more to it than just finding our bounds of integration and integrating our r with respect to theta. What we actually have to do is, well, let's take a look at this formula. Area equals the integral from a to b, where, I'll write it up here, theta ranges from a to b of 1/2 r squared d theta. R, of course, is a function of theta, so we can plug that in and square it. This would give you a very, very complicated integral. Most of the time, of course. I'll hop into an example, and then maybe we'll solve a different one, maybe with just a circle. So our first example says, well, we have the function r equals 1 minus 2 cosine theta. And so what's going to happen here is we're going to get a graph, of course. Let me just go over this again. When theta equals 0, so we're pointing this way, our r is pointing this way, we get a value of -1. So that's back this way. We get -1. Like I said, I never put my y's, x's and y's in there for some reason. Let's say theta equals pi over 2. We get cosine theta equals 0. We get 1 again. Let's say equals pi. We get -1. We get 1 plus 2, but remember, we're pointing this way. So we actually get -1 plus 2. We get -3. Let's say theta, once again, is 3 pi over 2, pointing down. We get 0 for cosine theta. We just get 1 going down this way, of course. So that's -1 in Cartesian coordinates. So what do we get here? We get this graph. I'm pretty proud of myself for drawing that one, actually, because if you watched the last video, I was definitely still getting used to drawing these. But what the problem asks us is we want to find this area. So what we need to do is find our bounds of integration. Now, where is this function at the origin? Well, there's 2 points, right? We have it coming in here, we have it coming out here. So when the function is at the origin, r has to equal 0. It means the radius isn't going anywhere, because theta always has a value going around. But r could have no value and be scrunched into the origin right there. And so we didn't really talk about this last video because we didn't really need to know it yet. So let's set r equal to 0. 0 equals 1 minus 2 cosine theta. This is going to give us cosine theta equals 1 over 2. And that's going to give us theta equals pi over 3 and 5 pi over 3. But, once again, we have to ask ourselves the question. Are we going from pi over 3 to 5 pi over 3? Or are we going from 5 pi over 3 to pi over 3? Well, here's the thing. Remember when we graphed our graph, we went like this. Out, out, and then back in. So what's actually happening here is that pi over 3 is somewhere along this curve. And so pi over 3 to 5 pi over 3 will be this outside curve. So we actually want 5 pi over 3 to pi over 3. So we're going to write down theta runs from 5 pi over 3 to pi over 3. And so just plugging this into our formula, we get the area equals the integral from 5 pi over 3 on the bottom to pi over 3 of 1 over 2. R squared is 1 minus 2 cosine theta, all squared. D theta. So that's our formula. If I was to evaluate this video would be about 10 minutes longer. But I'll give you the answer. The answer is 2 pi plus 3 root 3 over 2. I'm going to be honest with you. I'm not 100% sure on this answer. All of my other answers in every past video I've run through calculators online and such. But funnily enough, we've gotten to that point in calculus where we can't really ask computers that much or rely on computers, at least this day and age, yet. And so I'm pretty sure on my answer here, but yeah, it definitely could be wrong. So if you guys see something wrong with it, please put it in the comments. I'll pin the comment. And if you're questioning this answer, check the comments. But yeah, that's kind of exciting that as a class, I guess we could call ourselves, we have gotten smarter than computers because we know how to do this and some computers don't. So thanks for watching. I'll see you in the next video, hopefully, where we will be talking about sequences. We'll get into series and lots of tests, and finally finish off Calc 2 with some Taylor and McLaurin series. Thanks for watching.